I'd like to take a couple of minutes to review what we did in lecture today involving our definition of the reaction quotient Q and Le Chatelier's principle. So let's consider the reaction between H2 and N2 to give ammonia NH3. We know that we can write a ratio of products over reactants in the form of the equilibrium constant, where I write the products raised to the stoichiometric factor divided by the reactants. Here H2 cubed and N2. And at equilibrium, this ratio will be a constant equal to Kc. But we can imagine if we added, let's say, more H2 or more N2, then the quantity in the denominator would be a larger value than it would be at equilibrium, and our ratio would be smaller. In this non-equilibrium condition, we define that ratio as Q, the reaction quotient. In this picture here, we see that if Q is lower than the equilibrium value K, the reaction tends to move in a way that will reestablish the equilibrium constant K. In other words, the reaction tends to form more products. Likewise, if we have a reaction where the reaction quotient Q is too large, in other words, the product quantity is higher than equilibrium, the reaction will shift to reestablish K by forming more reactants. The idea that a system that's perturbed wants to reestablish equilibrium is known as Le Chatelier's principle. In addition to changing the concentration, we can also affect the equilibrium by changing the pressure when we're talking about a mixture of reacting gases and altering the temperature. Let's see what happens to the system when we make these changes. The effect of concentration. So we can think about equilibrium as a kind of a balanced situation between the reactant and product quantities. So this is not to say that the reactants and products have equal concentrations, but that they're in a comfortable or balanced state. So what's going to happen if we, for example, add more reactant? Well, our relative quantity of reactant in this case is above what it would be at equilibrium, and the product is below what it would be at equilibrium. So the system wants to shift to reestablish that equilibrium, and it will do so by lowering the relative amount of reactant and increasing the amount of product. That means that the reacting system will shift in such a way that reactants will be converted to product. Conversely, if we have an equilibrium system again, and we shift the equilibrium such that we now have greater relative quantities of product and lower relative quantities of reactant, we're going to shift the equilibrium in such a way that more reactant forms and the product concentrations are lowered. To accomplish this, the reacting system shifts to the left from products to reactants. Now let's consider changes in pressure and volume. Recall, these kinds of perturbations are only relevant when we're talking about gases. In reactions that don't involve gases, where the moles of the gas on the product and reactant side of the equation are the same, changes in pressure don't affect the equilibrium. They don't perturb the system in any way. Okay, so let's consider first a system where we change the volume by reducing the volume from some volume represented by this box to a smaller volume. In effect, we're compressing the gas. And when we do that, if all things being equal, the number of molecules being equal in both samples, we'll have more collisions with the sides of the container, with the container walls in the smaller volume, and the pressure will increase. So what happens to the reacting system? Well, the equilibrium is going to shift in such a way that will reduce the pressure. So in this particular reaction, we have 4 moles of gas on the reactant side and 2 moles on the product side. In order to reduce the pressure in this equilibrium system, we can shift that equilibrium to the product side. So what we're doing here is we're shifting the reaction to favor the side of the reaction with the least number of moles, least moles of gas. Okay. Now, in this example, that shift was towards products. But if we have a different reaction, a reaction where there are more moles on the product side than there are on the reactant side, the shift will be in the direction, again, of the least number of moles, in this case, towards the reactant. Conversely, if we increase the volume, and here I'm going to take my little sample here, put some molecules in there, and we now increase the volume, we see that our sample becomes less concentrated, the molecules hit the edges of the container less frequently, and the pressure responds by going down for that sample. If we have our system at equilibrium, and then we increase that volume, decrease that pressure, we're going to perturb the system in a way that will favor the higher pressure side of the equilibrium equation. So this is just the opposite of what we saw when we increased the pressure. We're going to shift our equilibrium value to favor the side of the reaction with the most moles of gas. In the case of concentration and pressure changes, the value of K, the equilibrium constant, remains the same. What changes, however, is the relative amounts of reactants and products, and those changes occur so that that ratio, products over reactants, can return to the equilibrium value. In the case of temperature changes, the actual value of the equilibrium constant shifts, and the way it shifts is a function of whether or not the reaction is endothermic or exothermic. Let's consider exothermic reactions first. In exothermic reactions, delta H is positive, and in the course of the reaction, heat is absorbed by the system from the surroundings. And if we actually hold a reaction that's endothermic, our reaction is maybe in a beaker, we'll feel that reaction beaker getting colder. So the way I like to think about how that affects the equilibrium is to think about heat as a reactant in this case. So heat is absorbed, it's entering our reacting system. So it's something we put in to make the reaction go forward. Just as if we add more reactant to a reacting system, we can think of heat in this same way. And that greater quantity on the reactant side is going to drive this reaction towards products. And we get a situation where the actual value of the equilibrium constant increases. Similarly, if we have a reacting system that's exothermic, it's a reaction that gives off heat. And we can think of that heat as a product. Addition of products to a system at equilibrium drives that equilibrium towards the reactant side. In this case, increasing the denominator in our expression for the equilibrium concentration and decreasing its actual value. Let's summarize. Remember, when we're thinking about perturbing the equilibrium, we need to think about how we express the equilibrium constant and how that perturbation is going to influence the value of this ratio of reactants over products, or products over reactants rather. Okay, so we can perturb the system by adding reactants or by removing the products. And in both cases, adding the reactants or making the amount of products less is going to reduce this value ratio of products over reactants, and in order to restore the value, we need to increase the relative amount of products. The reaction goes towards products. Likewise, if we have an equilibrium system and we reduce the reactants and increase the products relative to the equilibrium value, the reaction is going to shift towards the reactant side. Changes in pressure affect the equilibrium of systems involving gases. What we can say is the system responds to counteract the change in pressure. So, for example, if we lower the pressure in our reacting system, we favor a shift towards the side of an equilibrium expression that has more gas molecules. In other words, the high pressure side. That's to counteract the reduction in pressure. Conversely, when we increase the pressure, the system responds by shifting to the side of the equation with the lower number of moles of gas, or the low pressure side, again, to counteract the increase in pressure. And lastly, the effect of temperature. In situations where we're changing the temperature, we can think of that heat as a reactant or a product. In endothermic reactions, where delta H is positive, we can think of heat as a reactant. In other words, the system is taking in heat, and that's going to, like adding a reactant to an equilibrium mixture, going to shift the equilibrium towards the product side. In this case, the change in temperature actually alters the equilibrium constant by increasing the relative amount of products versus reactants, and the equilibrium constant goes up when the temperature is increased if the enthalpy change is endothermic. Conversely, for an exothermic reaction, we can think of heat as a product. Heat's given off by these reactions. Just as adding product would shift the equilibrium to the reactant side, heat, if we think about it as a product, does the same thing. And when we shift the reaction towards the reactant side, we increase the relative amount of the reactions over products. Our ratio then becomes a lower value, and K decreases for exothermic reactions. Okay, so that's all you need to know about how perturbing the system by changing temperature, pressure, or concentration will affect the equilibrium.